Welcome back to physical chemistry. I thought we would think about ultraviolet and visible spectroscopy today, so a lower energy region than we had last time. Let us first of all think about what possible transitions we could be thinking about. So we're not talking about the nucleus anymore, we're not talking about the central electrons anymore. We're now thinking about the bonding electrons that can be actually doing something. So if we take, let's take the simplest molecule we can think of, which would be hydrogen, because it's only got one bond and it's only got 2 electrons in it. If we look at its molecular orbital structure, we've got 2 orbitals that go together to make a bonding orbital and an anti-bonding orbital. The bonding orbital is this one in between, and the anti-bonding orbital is here on the outside. So now we can think of those two. So if we take 2 orbitals which could have 2 electrons in each, and we put them together, we end up with 2 orbitals that could have 2 electrons in each, but one of them has a lower energy, and one of them has a higher energy. And the higher energy one in this case has no electrons in it, because we started off with 2 electrons, one each. That's how we would construct it from quantum mechanics, and this is how we get, this is our molecule. And we can imagine that the lowest transition would be to kick one of these up into the next energy level. That would be the lowest energy transition that we can do. And we have then got this electron, and we've kicked it into this orbital, but we haven't turned it over. So that is the least that we can do to this molecule. We can see that the 2 electrons are spinning in opposite directions still, because we haven't rotated one. We can also see that if we do it on this diagram here, that there is no difference in energy between the starting state, with 1 electron in each of the separate orbitals, and the finishing state, which is 1 electron in the bonding orbital and 1 electron in the anti-bonding orbital. Now, I hear that your inorganic chemistry might not have gone so well this last semester, so let us just go back and go over that a little bit to make sure that we are on the same page to start with. So the concept of molecular orbitals, staying on hydrogen, would be that we take the orbitals of the atoms. This would be a hydrogen 1s orbital, and this would be a hydrogen 1s orbital. We add them together mathematically, and we end up with the same number of orbitals, but not necessarily the same shape. So if we take 2 1s orbitals and we add them together, we end up with a bonding s orbital in the middle, and we end up with an anti-bonding s orbital, which is on the outside. If we think of it as attraction, then we've got the positive nucleus surrounded by negative charge, and they can just float away. But if I have the positive nucleus with negative charge in the middle, then they will be attracted together. It's effectively plus minus plus. It's a magnet or an electromagnet. Not electromagnet. It's got electric attraction, electrostatic attraction, and so the molecule will stay together. If we take this particular version and we've got the positives inside and the electrons on the outside, then obviously they will be repelling each other, because the closest thing together is the 2 pluses, so they're going to push each other apart. So we end up with a good case and a bad case. What I drew was the energy levels. So we've got the energy levels of the s orbitals. We have the energy level of the bonding orbital, which is lower, and the energy level of the anti-bonding orbital, which is higher. We call it the anti-bonding orbital because it's the opposite of a bonding orbital. If we put electrons in there, and we can fill up the bonding orbital, which will mean that the 2 atoms will be connected together. That's what hydrogen is like. If we fill it up completely, then it doesn't bond at all. because the height above 0 of this one and the height below 0 of this one are identical. So if we have completely filled orbitals, then there is no bonding at all, and it's the same as not having any mixture at all. If we take the next shell up, we will have one s orbital and 3 p orbitals in 3 different axes, and they are what we think of as the base orbitals, but we can't make something like water or CH4. If we make CH4, methane, we can look at it and we can see that it's tetrahedral. It's got a hydrogen in all 4 possible directions, so it's completely symmetrical. So we need to make new orbitals that point in the directions that we expect, so that this theory and reality can agree. If we add all of these together and divide by 4, then we end up with new orbitals which have one big lobe and one little lobe, and they're tetrahedral. So they have the right geometry. The little back lobes don't clash. They do on 2 dimensions, but in 3 dimensions they don't. It's difficult to do it with my hand. We'll do it in organic chemistry. We've got all directions. If we have one, and if we leave one of the p orbitals out, we then have sp2 geometry. So this is sp3. We can also have sp2, which is flat and triangular, like that. So this would be sp2, and we can also have sp geometry, which is one like this, and then the two remaining p orbitals sticking out in the 2 remaining directions. We can start with any of those and then add them to the orbitals of the other atoms to make our new orbitals. So let's do that with ethane, for example. No, ethene. Let's do ethene, it's more interesting. Okay, so this is one end of my ethene molecule, and it's got 2 hydrogens connected to the carbon. It's got 2 equivalent sp hybridized orbitals here, the sp2 orbitals sticking out of this carbon, and they are connecting to hydrogen, and they're full, the orbitals, and they can't have any in the antibonding, any electrons in the antibonding state because they don't have enough electrons in. The carbon-carbon bond has the sp2 orbital the same as this. Let's draw it exactly the same. I should have drawn it the same height. Let's draw it slightly lower. So it has the same, and that has an antibonding orbital, which is exactly the same height. And then we have 2 other orbitals, the 2 possible, whoops, no we don't because we've used them up. I've drawn it too high. Come down a bit. So we have our carbon-carbon bonding orbital. This would be the sigma orbital, the single bond, and then we would have the second bond, the double bond, and it's got an antibonding orbital in there too. So let's label these. This would be a sigma. This is a sigma star. The antibonding orbital is labeled with a star for antibonding. This is a sigma between the carbon and carbon. This is a pi orbital for a double bond. That's how we denote those. It's got slightly different geometry. We'll draw that in a moment. And this is the antibonding pi orbital. So the pi star orbital to go with the pi orbital. What I wanted to define was the thing that is most interesting from molecular orbitals, which is the highest occupied molecular orbital, or the HOMO, which if we come down and down and down till we hit an electron, is this one, the pi orbital of our double bond. And we also are interested in the LUMO, the lowest unoccupied molecular orbital, which is this one, the pi star orbital. So the absolute minimum amount of energy that we can put into our molecule to get an electron transition would be to kick this one up to here. That's okay, it's fairly obvious in this case, but we might have other cases where there the highest occupied molecular orbital and the lowest unoccupied molecular orbital are the same one, like that. So now if we want to take an electron out, we would take this one. So we're doing some chemistry, and we would take an electron out, it would be this one, and if we put an electron in, it would go into the same orbital, just the other way around. In this case, if we want to take an electron out, it will be these two. So if this is going to react with something, it will give these two electrons away typically. And if we're going to dump electrons in, they will go into this antibonding orbital because it's the lowest energy orbital that we can access. If, like I drew it, if these were lower, then those would be the lowest unoccupied molecular orbitals, and that bond would be the most reactive. But in the case of this particular molecule, it is this one. It's the pi bond in the ethene. So this is the geometry of those orbitals. The electrons start off into p orbitals that are aligned with each other, in this case vertically. These centers, the carbon centers, the hydrogens are poking out over here, actually this angle. The bonding orbital is two clouds of electrons above and below the axis because it has the same symmetry as these two orbitals that it started with. And the antibonding orbital is 4 sections on the outside, in the same way that the bonding and antibonding orbital of the hydrogen molecule was in between and outside. This is effectively 2, one above and one below the plane of the molecule. That tells us an interesting thing. First of all, that the double bond is symmetrical and not that it's beside the other bond. It's actually on the outside of the other bond. The other thing that it tells us is from a chemistry point of view, if we're going to react with this molecule, we're going to either take electron density out of this part of the double bond, either from the top or the bottom, and there is no difference in which, because it's symmetrical. And we're going to donate electron density into the antibonding orbital if we want to break it by putting electrons in. And they would have to come from the top here, from the bottom here, from the top on the other side, or from the bottom on the other side, which is effectively between the two other substituents. In this case it was hydrogens, and they're pointing out and away. And so it's from above or below the plane of those two that we would have to attack it with something that is donating electrons. If we excite an electron into an antibonding orbital, we're kicking it from here into a place where it's out here. We've got a standard quantum mechanics mental problem that this orbital is in fact all the same. They're all the same. So if there's an electron in this orbital, it's up here and down here at the same time. It just sort of jumps from one to the other. It exists in both simultaneously. In this case, there typically aren't electrons in there in our antibonding orbital, but the orbitals are all the same. So we can donate energy in here, and it appears here, energy, electron density, and it appears over here just the same. It isn't very far, so the electron can just tunnel over there. It's a little bit weird to get used to, but that's where they are. We can't attack this bond from any other angle, so although you would imagine that attacking this bond from the side would be good, if we got some electrons that we want to poke into it, it's actually from this angle that we need to come. Now we come to another special thing. If we look at this particular molecule, which has got double bonds every other bond, in reality it's not got really double bonds every other bond. It's got one bonding system where the orbitals that are pointing up and down are interacting with each other all the way along the molecule, and it behaves like a wire. This molecule could theoretically conduct. We have to give it an excess or a deficiency of electrons to be able to conduct, but if we put electrons in the end here, we can take them out the other end because it's all one orbital. And that's because all of the carbons along this chain have the same pi bonding orbitals. That is why if we look at our benzene, we typically draw it with a circle in the middle, because either we imagine it to be a mixture of the two possible states, or we agree that there is no difference between the bond being here and the bond being between these two, because they've all got pi orbitals, which is on the top and on the bottom. So this is curcumin. It's a molecule that is in turmeric, or Curcuma in German, so that's why it's called curcumin. It has a benzene ring and an OH, and we can now count up where the p orbitals are. So there's a lone pair here, that's part of the ring. There's a lone pair here, that can also be part of the ring. All of this ring go down single, double, meaning that this is an sp3 carbon, sp2 carbon, this is an 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 sp2. This bond is a break, and the other part is a mirrored image of this side. So we have effectively that half of the length of this molecule is all one bond, but we can do something simple to make this better. We can remove this hydrogen, so we can put this in here. Oops, let's have two bonds. So we can change the bonding here. If we put that in there, that makes a double bond here and flips this one out, and then we can put the hydrogen back on over here. So we've effectively not removed the hydrogen, we've shifted it. This is called the enol form of this chemical. So effectively it's done an internal reaction with itself. Sorry, this is supposed to be a double bond O. That looks really bad. It's made it look even worse. I'll just change that. So it doesn't look quite so bad. There we go, it's a bit better. So now we've got our molecule, and our single double bonds go all the way through to the other end. Now we've got a different color, because the length of the bonds, the number of states that are involved, is nearly twice as high. Inside that bonding system, we can imagine that there are a whole set of different states where effectively all of the quantum states of the orbitals align, and so we get the lowest energy. Then we have a higher energy where they're in different organizations, and depending on which ones are filled and which ones are not filled, we can generate a highest occupied molecular orbital. So let's have it being this one. So we can have this one as our highest occupied molecular orbital, and the same one as the lowest unoccupied one, and our lowest energy transition would be this one, to knock one electron up to the next level in this. The more orbitals that we have, the more states that we pack into here, and the closer then they get. And that would mean that the amount of energy that we need to kick them up one level is lower. So the longer the bonding system, the longer the pi system, the redder would be the light that it can absorb, which is why the enol form of our curcumin, which has double the length effectively, it absorbs redder light than the keto form. What we typically see is a yellow dye that sometimes appears to be red. If it's yellow, it's absorbing in mostly blue and a bit of red. If it's red, then it's absorbing in blue and green. Another common dye, another common way to absorb light in the visible and ultraviolet region, but mostly the visible region, is complexes. So this is a complex of copper. If we dissolve copper chloride, for example, in water, we might end up with a complex like this with some chloride ions on it. This is copper 2+, we've got 4 chlorides, so it's still 2- in total. There is a little transfer of charge from the coppers to from the ligands, from the chlorides to the copper, and I've put 2 waters on there. I just made this up, this isn't real. There is a copper octa-aqua, one at tetra-aqua, and there are various other complexes that do exist. And they vary depending on what the concentration of chloride is, what the concentration of water is. What you may be familiar with is the splitting. So if we have the d orbitals, we would have 5 orbitals. 1, 2, 3, oops. 1, 2, 3, 4, 5. We have 5 orbitals. And depending on the geometry, whether it's octahedral or tetrahedral geometry, whether we've got 8 or 4 ligands on the outside of our metal, it will split the field, will split the orbitals, because you can imagine those d orbitals will either be pointing close to one of these ligands or they won't. If they're pointing close to one of these ligands, their energy will be strongly affected by whatever they're doing, so they'll either have energy donated into them, usually they'll be stabilized, or they will be pointing at an angle that doesn't align with one of the ligands, and then they won't be affected at all. What we discover is that they, depending on which one it is, they are divided into 2 groups. So we either get, this would be where they start, they either go 2 up, 3 down, or 3 up, 2 down. You can look that up because you're bound to forget even if I tell you now. I don't memorize it, I don't know it off by heart. I always forget and get it wrong, have to look it up again. Depending on the geometry, it's either 2 up, 3 down, or 3 up, 2 down. Because of the same physics that we had before, we're not allowed to gain energy in total. So if we fill all of them up, we have to have the same energy as if they're in the original orbital. But if we have an uneven number, so we've got 2 going up and 3 going down, then the 3 going down don't go down as far as the 2 going up, so that the average, if we fill them up, is 0. When we had a bonding orbital and an anti-bonding orbital, and it was the same number of orbitals going down and up, then obviously they're symmetrical, but here they're not symmetrical. The splitting coefficient, so the amount that they go down and up, is determined by how good the bonding is between the metal and the ligand. So we will see, if we get round to it, if we take a cobalt center, for example, and we take the chloride, then it appears to be one color because it absorbs light. And if we change it to the tetra-aqua complex instead, with 4 waters on it instead of 4 chlorides and 2 waters, then we end up with a different color, a different apparent color. And that can obviously only happen if there is a good organization of electrons in there to get it to happen. So if we have, for example, filled bottom ones or unfilled, let's just fill up the bottom. If we fill up the bottom with 6 electrons, then we can kick one up and down, so there is a possible transition to transition up. If we have completely filled, obviously, so the last element in the d block that has completely filled d orbitals can't do this transition, so it appears to be uncolored. The first element in the d block that loses that electron immediately to become charged also is not as colored as the other ones. So it depends what we can do, and it depends on the height of this transition. That determines what the color is. And whether you have 2 up and 3 down like this, or 3 up and 2 down, depends on the geometry of the complex. So those are the typical things that we would see. The other one would be a charge transfer from the ligand to the complex, to the metal. So we can also knock an electron out of here directly into the copper. So that would effectively be an electron transfer into one of these orbitals from an orbital on one of these ligands. So now we've got 2 possibilities. We either have a bond in a molecule, or we have a metal center that has possible energy levels that are generated by the shape of where it's sitting. So we can put this copper, for example, also inside a crystal of something else, and it will also generate colour, and we will make exactly the same thing.